Welcome to Telegeography Explains the Internet, the show that explores the business behind all of the ways humans stay connected around the world. So first, if you've been a subscriber of the show, then you'll notice that our name has changed. The WAN Manager podcast is now Telegeography Explains the Internet. During the course of the past 3 seasons, we started to realize that all of our research areas at Telegeography, which go well beyond my particular focus on corporate networks, had introduced us to a wide range of fascinating experts across many segments of the telecom business. So our focus now on the podcast is going to be about really anything that is wholesale or enterprise transport and networks, data centers, the internet business, and really anything related to moving data around the world. So I am your host, as always, Greg Bryan, and to kick off this season, we're going to go deep into the supply chain, much deeper than we've been in previous episodes. My guest today is Dr. Michael Lebby, who's the CEO of Lightwave Logic, and we had an illuminating, pun intended, conversation about building a better mousetrap in the light switching world that makes optical transport possible. So I'm going to get to my interview with Dr. Lebby shortly, but in order to contextualize that conversation, which is further down the supply chain than we normally talk about at Telegeography, I thought I'd invite my colleague Rob Schult on to just talk about some of the impacts of this potential change in technology on the actual telecom business itself. We get into that a little bit in the interview as you're here, but really, Dr. Lebby's expertise is in the plumbing, as he puts it, and not necessarily in the broader market as the impacts for the telecom industry go. So, Rob, thanks for joining me for this little quick intro.
Great to be with you.
All right, so Rob, I just wanted to ask you first, you listened to the interview that everyone's going to hear in a few minutes. What struck you as the potential biggest impact of Lightwave Logic's new technology?
Yeah, I mean, I think the thing that I found fascinating was that it was sort of a shift from like optics and speed to materials, right? So what he talks about is sort of a improving materials to reduce power consumption, bottom line. And I think, over the years, increasing speeds has really required increased voltages, subsequently consuming more power, requiring more cooling, and that's just escalated, right? As the transmission systems have grown, as data centers have grown. Both these, particularly with our current energy markets, which I think we're all aware of, are major costs of operation, and that impacts everybody. So I think that's sort of the first takeaway. The second thing that I thought was really quite interesting was with these new materials, it reduces the need for complicated encoding schemes over the optical signal, right? And one of the topics, we talk about all the time when we look forward and these huge requirements of data on systems is the Shannon limit. Like, will we hit that?
Yeah.
And I think what he tries to present is that by improving materials and reducing the need for some of these electronic encoding schemes, you create the opportunity to increase transmission speeds without having to change anything else, and at least buy more time, I think is what he said, to improve things going forward. So that I think that's a huge takeaway.
Yeah, exactly. Like in the Econ 101 sense, we're going to increase the supply, and what happens from there, right? So we've seen this before. You and I, we've been looking at transport prices for a long time. Can you take us through maybe some previous step changes in pricing driven by equipment advances and what that looked like for the market then?
Sure. Well, I mean, I think, Greg, when you and I both started, we were talking about SDH and Sonnet, right? Like that was the transmission standard of the day, and optical wavelengths with
155 megs, right? Yeah. So
yeah, exactly.
622.
STM1s, STM4s, OC3s, OC12s, all that. But but obviously, that was a solution that had expensive signaling on top of it, right? It provided a protection scheme, but as things became optimized, that became unnecessary. And I think,
Right.
if you talk to every service provider in the world right now, they would prefer to move away from that because
Hmm.
they're lower cost opportunities. So the shift away from that sort of standard into a purely optical standard was one transition that carriers have made for cost savings. Uh, and the other thing too is that we shifted from a 10 gigabit standard to a 100 gigabit standard.
Right.
And the idea there is that over the same system that has a fixed cost, or the same fiber lay that has a fixed cost, you can put more capacity down it.
Hmm.
And that the whole idea is cost per megabit, right? So that allowed price reduction effectively. You can more
Yeah, and that
efficiently put more
cascades,
capacity.
right? So even if the
Exactly.
primary, big transport pipes have gone down in the cost per bit, even someone selling 10 megs somewhere goes down in cost per bit because it's all break bulk from there, right? So
Exactly. And I think the thing that we see is this hasn't ceased, right? So
right.
in development right now are deployments for 400 gig systems. I mean, they're actually operationally both, in the lab, but commercially on some routes. And there's expectations that 800 gig and
Mhm.
potentially higher could be rolled out in the future. So again, putting more capacity down on a system that has a fixed cost is one thing. The other bit, which we've not really seen, and this is directly related to Dr. Levy's presentation, is that the cost of power to now hasn't really been a huge driver for the cost of a wavelength, right?
Right.
Energy prices have been fairly stable. You've definitely seen content providers and data centers try to put resources in places where power is cheapest, but
Hmm.
fluctuation or variability and power prices have not really affected transport or IP transit prices. It's a good question on whether that is going to remain the case, right?
Right.
Because we're not seeing modest increases right now. We're seeing massive increases now in energy costs. And I think the best thing that I would take away from Dr. Levy's presentation is that anything that we can do to reduce power costs, or the power required to generate signal, to reduce cooling costs, that can have a positive
Hmm.
impact and give opportunity to future reduced prices.
Yeah, through the whole data center ecosystem. Data centers are, of course, always networked to each other, and so yeah, there's potential there. So if we have this potential to, one, increase the supply, maybe two, sort of, even if it's not directly on the transport leg itself, but just decrease power utilization across like the kind of data center telecom business, is there enough demand to keep prices from tanking? Prices have always fallen, but they've never collapsed per se, right? And that's because demand has always been pretty much on the heels of supply changes. Do you still see that being the case?
I do. Yeah. I mean, I think if anybody has been to any of our presentations, you see you see the curves where demand will continually grow, and then we try to map out requirements for new infrastructure that has to be put in place for that demand to be fulfilled.
Right.
I think we still anticipate massive demand. Certainly on a percentage basis, maybe it's slowed, but on an actual terabit basis, it's still massive. Like, I mean,
Hmm.
it's complete systems over a number of years, right? You
Yeah,
can't
yeah.
just
One
add
percent of a
more.
terabit is a lot of data, right? So,
Exactly. You're
yeah,
not just
yeah.
lighting more wavelengths, you're adding new submarine cable systems to fulfill
Right.
it. I think, the demand models that we have reflect things like internet backbone demand, content provider demand, research and education, and governments. I mean, I think the thing that's interesting with this tech, right, is that yes, you can build a new cable system. Yes, you can put more fiber down it. But to a point, you have a limit to the amount of capacity that you can put, right? When you talk about the Shannon limit. And what this sort of technology does is it, starts to give opportunity to maybe increase the amount of capacity you put. So, yeah.
Yeah. Also, I think as they're going to find out in a few seconds here, he's very clear. So it's a technical conversation, but it is one with very good and adequate analogies and ways for you to be able to understand what we're talking about. So it won't go over our normal listeners' heads, I don't think at all. So thank you, Rob, for joining me. And with that, let's get on to the interview. Okay, so I am joined today by Dr. Michael Lebby, who is the CEO of Lightwave Logic. Michael, thanks so much for joining us.
Thank you. It's great to be here and looking forward to the chat.
Yeah, so we always start out with kind of an introduction of our speaker. I was looking over your very impressive and varied CV. You'll have to give it a brief treatment because it is a long CV. But could you just give us a little bit of your background so the audience can know who you are and where you're coming from?
Yeah, absolutely. I'm a techie's techie, so I've spent my career, I guess it's close to 40 years, although I don't have much gray hair anymore.
That's okay.
Um,
Yeah.
Born in England, London, and I went to British universities. I have two doctorates because over in the UK you're allowed to get two doctorates, a higher
Mm.
doctorate. And first started working in the British government in their version of the Bell Labs. It was at
Mm-hmm.
the time called RSRE, Malvern Royal Signals and Radar Establishment. Sounds very complicated. But right after that, I moved to the States and worked at Bell Labs in New Jersey. And the
Mm-hmm.
technologies I worked on were the semiconductors that were going to go into the optical network, or the internet as we call it. And
Mm-hmm.
these semiconductors are actually made out of indium phosphide and gallium arsenide. And these are materials at the time they were using for lasers and photodetectors. So if we think about the internet
Right.
today, it's a fiber optic network, has a laser at one end that sends out light and has a photodetector at the other end to receive light. And then from that point, I moved to Motorola's corporate research labs in Phoenix, Arizona, and rose through the ranks of R&D. And at which point, I decided it was time to go start some companies. So I've done a
Mm.
lot of small company startups in this type of space, but really focusing on the transceiver, the transponder module, the
Mm-hmm.
subsystem. So that's components all the way up to the subsystem. I haven't actually been a network architect, and that's really not my cup of tea,
Right.
but I certainly understand the
Mm-hmm.
impact if you make really cool, high performing components and how they would change the performance of the whole optical network.
Yeah, that's a great point. That's kind of how I was thinking to introduce our topic, generally speaking, today, which is that this is Telegeography Explains the Internet. We used to be the WAN Manager podcast. Normally, we're talking to the folks that sell lit service, that sell maybe the software or equipment that facilitates lit service, or the folks managing the networks. You're maybe even a couple layers of abstraction underneath that at Lightwave Logic and your entire background as you just described. Could you just give us those? Well, the show will be about specifically what you're doing, but just the very brief overview of where you fit into that ecosystem of we're usually talking about like layers 1, 2, 3 of optical networks, but you're where do you fit into facilitating that business essentially?
So we are working on the pipes. I mean, if you consider an analogy of the motorway or the freeway system,
Mm-hmm.
we're working on the cars that go on it or the vehicles that go on it. So we're working on the optical devices. These are the devices that helps the data flow more smoothly, faster through the pipes, through the fiber optic networks. So most of my career has been focused on how do you get optics to really work well within the fiber optic cables.
Mm-hmm. So switching the light to facilitate the pushing of the bits essentially.
Absolutely, yeah. And so if you think about it, you've got a laser at one end and it's sending out light, and you've got to modulate that light. So if I just put my hand up for a second and assume this is the laser and it's sending out light in a light beam, and that light beam is going down the fiber optic channel. What we have to do to send data is to create ones and zeros. And so a
Mm-hmm.
very simple way of doing that is you block the light, you got a zero, and you unblock the light, you got a one. Now, a device that does this, actually, you can see it will form ones and zeros just like a square wave, castellated waveform. The
Hmm.
faster you do it, the more speed, the more bandwidth you can send down the fiber. And that's the type of thing we see when we have, the internet connected to our homes. We want more bandwidth. We want more data coming in. And
Hmm.
so down at the optical level of the optical network, we've been focusing, and most of my career has been focusing, well, how do you get those devices to send data faster and lower power?
Right. Right. Absolutely. So, I end up explaining the internet to people often, and I always start with, if you can understand the concept behind a telegraph, you can essentially understand the internet still, right? So, the fundamentals, and so if I'm reading you there, it's like, it's a little guy with his visor cap on in the 19th century, pushing that button with sort of beeps, right? Is essentially doing the job of your widget, right? That is turning that beep on or off. Is that a fair way to put it?
That's a fair way to put it. In fact, my first visit to a telecom switch was in Holborn in London in 1978, 79, something like that. And as you walked in the building, these all mechanical relays doing the switching, as you just indicated. They're just
Hmm.
clicking like this, and
Yep.
it was just like being in a forest of crickets. And
Right.
that's what
Yeah.
it was at the time. But if you go into
Hmm.
one now, you go into a data center, it's really quiet, and all you hear is the air conditioning fans.
I was
It's
going to
very,
say
very different.
the hum of the massive HVAC system. Exactly. Yeah. Absolutely. So at Lightwave Logic, you're essentially facilitating light switching. Those of us in the industry, and maybe you could even sort of explain this much better than I could, but a lot of us in the industry are going to be familiar, at least with the terms of like a pick card, right, and that sort of thing. If that's what you're doing, what is it that you're doing differently than has been the case for the last, say, 10 years or so? I'm remember I used to cover a lot of optical pricing, and that used to be a big part of my job. I always have behind me our map of submarine cables, and when there's a way to get more bits across a submarine cable, the supply has increased and prices go down. So that's how it affected my life. And so I remember when certain companies would come out with a better pick card or whatever the case may be. Where do you fit into that sort of curve of innovation?
Right. So let's go back to that little simple analogy over. Here's a laser. Lasers are typically made out of a semiconductor called indium phosphide, and they're sending out light because indium phosphide is a material. Once you apply a voltage, it sends out light.
Hmm.
Silicon, you sort of can do that, but nowhere near the performance to replace indium phosphide. So although research in silicon to generate light has been ongoing for decades, it's still a huge challenge. So you've got this laser diode sending out light, and you need a modulator to modulate the light, to switch
Hmm.
the light, to modulate the light. Well, the incumbent technologies in the optical network for the last 40 years have been semiconductor based. And so,
Hmm.
for example, like submarine cables or trunk lines across the country, the material to do the modulation has been either lithium niobate, it's been indium phosphide. So lithium niobate 20 to 30 years ago. And then over the last decade and a half, it's been indium phosphide to do this.
Hmm.
And more recently, in the last decade, it's been silicon. And so you can see there's been sort of a choice of moving the semiconductor technologies to increasing performance. Now, as we look at those technologies and we look at their performance that they can get today versus what the operators, the telephone, the telecom, the data center folks want to see, it's sort of sunsetting in terms of performance.
Right.
And we've really reached the limit of speed. And if you do increase speed, you have to really increase the voltage.
Right.
Now, if you
Right.
increase the voltage, the power consumption goes up. And if you think about the big Achilles heel of the hyperscalers today and the folks that
Hmm.
do all the switching of the traffic, it's power consumption. We already talked about HVACs and air conditioning to
Right.
try and cool these buildings. I mean, it's a huge problem. So any way these folks can reduce power consumption is going to be good for them. And in fact, what they're looking for is something that modulates light really, really fast, but at
Hmm.
very low voltage, i.e., less
Hmm.
than 1 volt. Now,
Hmm.
what's the benefit of doing something like that? The benefit of doing something like that is yes, you can get lots of data across if you can switch faster. But if you can do it at low voltage, then you're saving power, you're generating less heat.
Right.
And you don't need to have independent driver chips, for example. So you can actually drive these devices directly from your DSP or your ASIC
Mm.
or from
Hmm.
your line card. What that does is it's not only the benefit of the cost of this fast little optical widget called a modulator, you're giving the architects of the network some freedom to how they want to redesign or more optimize their design to send data down the fiber optic cable. And
Hmm.
one way to explain that is if you look at the semiconductor modulator technologies over the last decade, they really haven't improved in device performance. So their bandwidth, which is a technical term we use for the device speed, it's been roughly 25 to 35 gigahertz.
Hmm.
With that, you can generate a 50 gigabit per second signal using your standard PAM2 NRZ type signals. That's your
Yeah.
castellated waveform, your square wave. If you use a PAM4, which is actually more encoding, it's a staircase, um, you can double the speed, but you lose out on your signal to noise ratio, and
Hmm.
so folks have been using electronics to improve the optics, and that's
Which
interesting
consumes more
because
power, right?
which
So
consumes
yeah.
more power because when
Yeah.
I entered the field 30 odd years ago, optics was super fast.
Hmm.
And I thought, wow, this is really cool. But today, in today's environment, we use electronics. We use these complicated DSP chips to actually improve the optics. And what hasn't changed in the last decade is the speed of these modulators.
Right.
And so the time is right for a new technology. And that's really where I come from in Lightwave Logic.
Well, certainly. I mean, we're having this conversation in September 2022, and there's talks and Europe with the Russian Ukraine conflict and all of that of how are we even going to get adequate power, and people look to the hyperscalers as a large power consumer as part of the sort of carbon crisis. So I think certainly it's got to be on their minds that if we can cut power in facilitating transport between data centers or across submarine cables. That certainly sounds compelling. How are you actually achieving that? So you started out with the sort of what materials you've been using over the past 15 and 20, 30 years. What's different now?
So the magic sauce, the materials we're using at Lightwave Logic are what is known as electro-optic polymers.
Hmm.
So these are organic chemical materials. They're not semiconductors at all. And in fact, yes, let's think about polymers for a second. Polymer, because it's not a semiconductor, where do we see polymers every day and we don't think about it? Well, probably the computer screen I'm looking at is an OLED display. It's an
Mm-hmm.
organic LED display. It's probably our TV. My TV downstairs is probably an organic LED display, and so is my mobile phone. And so that has actually displaced LCD displays, which we all used a decade ago,
Right.
because of the performance of the polymers is incredible. Now think about it this way: we do electro-optic polymers to switch light, to modulate light like this. So our polymers do not emit light like the OLEDs. OLEDs are
Mm.
designed, their chemical composition allows them to send out red, green, blue, so you can produce a color display.
Right.
Ours are designed, our organic chemists in Denver, Colorado, designed to how do you maximize the modulation of the light at very low
Mm-hmm.
power?
Mm-hmm.
So it's a similar organic material, except it's got a different function. And with this material, if you apply it to the fiber optic space, Mother Nature really works with us. And you've got naturally fast speed, you've got naturally low power. And it's really exciting because we have a technology that is just going to fit perfectly as the architects for the optical internet look at
Mm-hmm.
how to reduce power consumption over the next decade.
Yeah, I mean, this is from the technical aspect. Going over, You've explained it very well. I have to just believe you. It's like I can't understand the actual parameters, and I'm sure is the case with many listeners, some of them are sort of deeper down at that level. But it certainly sounds like a potential next step change in sort of the cost of transmitting data across the world. So in that light, I'm curious if you can go into who your intended market is. I mean, it seems to me fairly obvious that your intended market would be the equipment manufacturers who make the boxes, the lasers that sit on either end of a fiber optic cable. Where else do you fit into that ecosystem, and what are you actually trying to sell to the broader market in that sense?
Yeah, no, this is a very interesting question because if I, started the company 20 years ago, with a horizontal market, then you make components and you sell the components to
Hmm.
the next level up in the value chain. Well, today, a lot of the customers, the hyperscalers, are actually vertically integrated. They do everything
Right.
from the chips to
Absolutely.
the package to the transceiver module, which is your transducer module for taking your light to your electronics and back. Put that into the line card. Line card goes into a system, a switch or a router. So yeah, they're doing everything. And
Hmm.
so how do you put together a business plan that services those in a way that can really like leverage what they're doing and give them value for their products? Well, our business plan is both selling products, it's licensing the technology, and also doing tech transfer. And
Hmm.
if you want this technology to be like OLEDs, like on displays and TVs and things, that's already ubiquitous. How do we make
Hmm.
our technology ubiquitous like that? And that's a challenge. And so we are working with silicon foundries. Silicon foundries are big factories that run lots of wafers, and they're really
Hmm.
interested in the optic space because that offers an opportunity to run more wafers because
Right.
that's their business. Um, Customers will work with the foundries, and customers will work directly with us. And customers was, as you say, will work with directly with OEMs that interface with
Hmm.
us. So it's not just a very simple, you are my customer and I'm going to serve you. It's actually quite complex. And
Hmm.
for that reason, I think as a company like ourselves, you have to have a flexible business model. And in doing that, you can service the different needs and requirements of all the customers. But to do that, you have to have a pretty strong patent portfolio and a
Right.
good
Of
good
course. Yeah.
position in
You're
your
not
market.
just selling widgets, you're selling technology, information as well, right? So.
Exactly. So, we definitely will be designing the formula, the chemical formula of the polymer material ourselves and scaling that ourselves. But to actually make the devices, the foundries will make the devices, and then the foundry will have our technology on their recipe. If you like, product list,
Hmm.
they
Hmm.
could actually explore different markets and things because right now we're just exploring just the fiber optics market.
Right. So that's an interesting question. So obviously, my chief interest is the fiber market, but you're saying that this polymer technology could implicate a lot of other places where we're switching light essentially, right? That's not just telecoms per se.
Exactly. So, we're just focused on the fiber optics communications markets right now. But, we're not a huge company and we want to be focused and we want to
Hmm.
actually have a big impact. But we've had a lot of inquiries and interest from what I would call optical wireless markets. So what's an
Mm-hmm.
optical wireless market? Well, it's like LiDAR in automotive.
Hmm.
Everybody's talking about every car in the future is going to have a LiDAR on
Absolutely.
it,
Yeah.
right? So we're talking about 3D sensing. I mean, in the mobile phones, we have structured light sensing, and that's
Hmm.
going to go greater distances. And so we've got projection displays. That's all optical wireless. And so if
Right.
you start thinking about where optics plays a role, it's not just in the fiber. In our lives, it plays a role, as a wireless. What do I say? A wireless technique or a wireless sort of facility. And that's
Mm-hmm.
important because you start looking at some of those markets, they're huge.
Right.
And if
Yes. Consumer IT is a bigger market than telecoms, I will admit, certainly. So yes,
it's
absolutely.
huge,
Yeah.
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 And so from that standpoint, could we as a company, Lightwave Logic, take on all these markets? Probably not. I mean, it's just a
Hmm.
lot to
Hmm.
take on. So
Right.
if a foundry or an OEM says, "Hey, we like this polymer stuff. Can we license it?
Right.
Can you transfer your recipe from your little fab into our big fab so we can add it onto our list so we can have our own customers that may be in the automotive space or some display space?" I think that's a great business model for us
Hmm.
because what it does is it allows polymers to become ubiquitous.
Yeah, and sort of again, bring it back to my perspective, the perspective of most of the audience listening to this is, and I know that, you're not sort of focused on this part of it. Of course, you're focused on making that particular piece of the plumbing function better. But the implications are that if you get that technology out there faster, then we see the gains in efficiency for power and bandwidth consumption appear in the market faster, right? So obviously, if you were staying sort of vertically integrated in that sense, there would be a time spent to penetrate that market. Whereas if you're kind of saying if we license that to a whole bunch of different folks, they can then determine sort of how this fits into their ecosystem, and the technology itself will spread faster. So it seems like this could be changing the way that we think about telecom limits in the near future. What kind of timeline are you looking at? So, is this something where you're going to market with fiber optics now, or is this sort of will be ready for service in the coming years, or where are you on that timescale?
So, we've given some level of guidelines earlier this year in terms of our progress with the company and the technology. The thing we're pointing to folks to, if you want to watch our progress and see how we're doing, is
Hmm.
look at our um, interaction with the big silicon foundries. So we
Mm-hmm.
started
Hmm.
that interaction a year ago. Now, why would I suggest looking at that? Because that is really if we can port our recipes, our process recipes of making these devices into the big foundries, then you can get to scale quickly and
Hmm.
efficiently. Now let's think about this a second. I mean, what's a recipe, right? A recipe is how we make this optical device, and it's normal fabrication techniques that you use in the silicon world. So there's nothing new there. But if you got your mother's recipe that you've been using for the last 40 or 50 years, and some
Hmm.
special recipe you make in your kitchen, and then somebody says, "Oh, I really want that recipe," and they make it in their kitchen, it may not work the same because the temperature of the oven
Right.
might be slightly different or the calibration of the knob is different. And so when you port recipes from one place to another place, you have to make sure they get done right and
Right.
the
Of
outcome is
course.
right. So we're in the phase right now in the company of porting our recipes to the foundries. And
Hmm.
once that process is finished, then we'll be in a position to gain scale and volume in a way that we really want to have. And that's one of the last big pieces of the pie in
Hmm.
terms of, if you want a technology to be popular, you may have your business model, but you've got to have the availability and the capacity to serve people when they need it. And that's what we're working
Absolutely.
on right now. So you'll see a lot of updates over the next, I guess, 12 to 18 months on that front.
Excellent. Yeah, I look forward to keeping track of it. One last question I have, and you can tell me if this is outside of your purview because it might be a sort of layer up from what you're working on. But something we've heard come up in the optical business the last few years is that we're getting to the point where we're pushing up against Shannon limits on optical transport. Is this going you're talking to a layperson here, right? So does this change the Shannon limit itself, or not run it, sort of in other words, like if the Shannon limit is there, it's not a fixed number per se, and this can make more bits possible over the same channel, or are you going to be running up against the Shannon limit once this is deployed?
So yeah, so channel limit is a pretty complex term to understand. And
Believe me, I especially as me trying to understand it,
so,
no doubt. So yeah,
so our technology is really helpful to give us more time before we reach the channel limit.
got it.
So what
That's
we're
what I'm
doing with
after.
that,
Yeah. Hmm.
what we're doing with that technology is we're buying some buffer. And what's the easiest way to explain that? The channel limit is when you've got a signal and it's your maximum capacity you can send down the fiber with a known signal to noise ratio. All right. So what's that? That's the difference between the 1 at the top of the waveform and the 0. And so when that gets close, then there's no signal to noise, and then you can't detect any signals at all.
Right.
And so it's the maximum capacity of keeping that as wide as part as possible. Now, when you have faster optics, then you don't need to go to the complicated encoding schemes. And it's the complicated encoding schemes that are used today by the electronics to get to the information capacity. And that's what's driving a lot of these networks today towards the channel limit. If you have faster optics, you can take a little bit of relief on the electronics and you drop down. So you're not at the channel limit. So faster optics is actually more helpful. And so you can give the architects, that flexibility to say, if you want to stay well away from the channel limit, keep the electronics to a minimum, reduce your power consumption, and then get your capacity up with faster optics and good signal to noise ratio. Now, some architects are going, you know what, that's not enough. I want all the electronics. I don't care about power. I want to go as fast as possible. And so with faster optics, you can get more data capacity per signal to noise ratio because you could probably get away with an encoding scheme that is not as complex. Because the more encoding schemes you have to get more data capacity means your signal to ratio goes down. So the simple answer is our technology gives you a lot more headroom, and it allows the next generation systems to be designed quite effectively without hitting the channel limit or even getting close to it.
Excellent. I got to hand it to you. I understood that. So you did a really good job of boiling that down for a general audience. So much appreciated. Yeah. So Michael, this has been really interesting. I'm truly excited to kind of see how this plays out over, like you said, the next 12 to 18 months, and look forward to potentially some of these impacts. It's going to be interesting to watch. Just in conclusion, I want to give you the opportunity if anybody wants to keep up with your work or you, is there a way that they can do that, especially as we're watching these advancements unfold?
Absolutely. There's a couple of things to watch for. We have a pretty good cadence of PRs. I mean, if you look at the number of PRs we put out, I don't know if it's every 2 weeks or every 3 weeks, but there's regular PRs, and they give a lot of guidance and progress. I give a lot of presentations, both at bankers conferences and also, like, for example, next week. The reason I'm over in London today is I'm heading to Switzerland next week for the biggest optical communications conference in Europe. It's called ECOC, a European Conference on Optical Communications. And I'm actually presenting a paper there on our technology progress. And I'm also participating in the conference in a number of different sessions. And also the US one, which is called OFC, that stands for Optical Fiber Conference. That's where all the techies get together and they talk about the latest and greatest in speeds and power consumption and things. And that usually happens every March. So those are the two techie conferences to look out for. Plus there's our normal presentations and PRs that we put on our website. So it's pretty easy to follow. And if your audience has questions, feel free to reach out with our IR folks, and we'd be happy to help out.
Yeah, excellent. All right. Well, thank you so much for joining me. It might be great to catch up sort of once this is out there and operating, and we'll see how everything's going. So,
no, thank you. I really enjoyed the chat.
Yeah, absolutely. All right. Cheers. Thanks for listening. Telegeography Explains the Internet comes from the experts here at Telegeography. It's edited and produced by Jane Miller, and it's hosted by me, Greg Bryan. And I also wrote that theme song you're listening to right now. To learn more about our data, jump over to telegeography.com, and we'll see you on the internet.